अटेंडर्स का कोर्स या वर्कशॉप टेक्नोलॉजी का कोर्स किसी ने ऑनलाइन अटेंड किया होगा, तो तब तो सिर्फ मेरी आवाज़ सुनने का दुर्भाग्य आप लोगों का था, आज मुझे देखने का भी दुर्भाग्य आप लोगों का है। तो एक्चुअली मेरे पास कवर करने के लिए एक्चुअली यहाँ पे बहुत कुछ है इस वाली क्लास में। बेसिकली मेरा जो उद्देश्य है इस क्लास में वो ये नहीं है। अच्छा, हिंदी और इंग्लिश? हिंदी या इंग्लिश? इंग्लिश, ओके, ठीक है, all right, English. Sorry. So my objective in this class is not so much to take you through a very specialized technical overview of high-speed rail, and certainly no detail. My objective here is to take you through a certain amount of developmental steps of high-speed rail as they happen, when they happen, and also the standards, the major technical standards as they stand at the moment. And this is also with specific respect to, or with specific reference to, the Mumbai Ahmedabad High-Speed Rail project, which is based in no small part upon the E5 series of the E5 Shinkansen series, not the N700, the E5 series, which is in turn based the product of about 40 years of research from JR East and RTRI. Now, I had the great good fortune of being able to go to Japan for my master's course at the Tokyo Institute of Technology and conduct my research for 2 years in high-speed rail. While basically my research was more specifically upon the maintenance, upon the shell maintenance of high-speed rail, more specifically the maintenance of the welded car body joint, which is of aluminium. So I will take you through that as well in a very brief form. So so as I said, as I want to emphasize here, what we're looking at here is the big picture. Now, just because I am up here on this stage and all of you are down there in the audience, please do not think that you should sit back and relax and listen. That is very good, but you've all had tea, you've all had a very highly technical presentation this morning. My presentation is slightly, in fact, much less technical and much more general, and therefore I hope that we can interact much more and much more freely on these topics, because all of us have experience with some amount of train sets, or with some amount of high-speed rail, or some amount of railway technology in general. We are all, after all, boosted. So please interact, please ask questions, please give me your feedback, your input, and nobody in this room has all the answers. Nobody in all of India at present has all the answers. That's why we are buying a technology from the Japanese. So so there should be no complex over here. Please, let's keep this two-way. So when we talk about high-speed rail, let's go with let's take the first things first. Let's begin at the beginning. And my beginning is that I am no expert, as I have been trying to explain to you. Yes, I have gone to Japan. Yes, I have visited their workshops. Yes, I have visited visited and attended several seminars by ADBI, by JREs, by RTRI, by CoRail, etc., both in physical mode and online. And yes, I have been fortunate enough to go and visit and see their train operations and their maintenance paradigms, along with whatever little of their design that they are willing to share. But high-speed rail in itself is much more than a few months or a couple of years worth of experience or worth of information, and it is certainly much more than what we can talk about in whatever 1.5 or 2 hours that we have here. So it is something that is, I mean, as I said, it is even the E5 series, which is outdated in Japan, which we are buying here in India for the Mumbai Ahmedabad high-speed rail corridor. That series itself is the result of about 40 years of R&D. 40 years of intensive, dedicated R&D by one of the finest railway research institutions in the world, which is the Railway Technology Research Institute of Japan. So, when we are talking about decades of scholarship, and when we are talking about several generations of several experts in several fields, to say that we are going to study high-speed rail here is not the correct approach. What we can try to do, and what I am very interested in doing for all of you here today, is to increase your interest and sharpen your curiosity. That does not mean that that any of us becomes an expert. In fact, we must all realize just how deep the water is before we proceed any further. So, so when we talk about high-speed rail, first question that we want to ask is, why do we talk so much about high-speed rail? That is to say, why is high-speed rail so important to all of us? Why is it that that everybody from Prime Minister Modi to Taiwan's premier, to the chancellor in is it the chancellor? Is it the prime minister in Vietnam, or Singapore, or anybody? Why are all these emerging? Why are all these highly developed as well as very fast emerging economies so interested in high-speed rail? And more importantly, what is it that makes it that makes it more than any other project? We don't hear so much talk about things like new any other infrastructure project. We don't hear so much about things like track doubling, which was made much of, but we know about it because we have the railway service. We don't hear so much about practically any other project as much as we hear about digitization and high-speed rail, and I shall show you how they are related later. So before I proceed, I would like to, all of you can just read the slide, and then let's have a little bit of conversation about why high-speed rail is so important. So can anybody tell me why high-speed rail is so important?
Sir, up to a certain distance, it is the best way worldwide, most time efficient way worldwide to reach from point A to point B.
Okay. High-speed rail is time efficient. Okay, that's one thing. But again, that is a benefit of high-speed rail. Why is that so important to the nation? You are there, but not quite there.
So, is it also because to lessen the load on the domestic airports?
To reduce the load on domestic airports?
Yeah.
Then why has the Prime Minister just inaugurated a new airport in Noida, which is the 5th in UP this year?
Sir, like the Mumbai-Ahmedabad project, the cities that project connects, when this comes from ground,
Yeah.
it will be very beneficial for the other cities like Surat and Ahmedabad, because people
Yes.
there can commute in such a feasible duration of time that they can stay there and they can come to Bombay. They may be commuting daily for office or maybe for business purposes. So basically
Yes.
the productivity of people at large of that cluster.
Thank you. That is the exact correct answer. And you have used a very important word there, productivity of that cluster. Yes, that is exactly the reason. As Mr. Shubhranshu touched upon in the previous presentation, Japan's main island, where the Tokaido Shinkansen was originally launched, was, up to the 60s, it was a collection of large villages and paddy fields. In fact, they were growing 3 crops of rice a year, and nobody in Japan was very much interested in anything much beyond that, outside of the urban centers of Tokyo and Osaka. However, in about 20 years, Japan was in fact, at some point in the 80s, it actually crossed the United States for a short period of time to become the largest economy in the world, and even today it remains the 3rd largest economy in the world, with a population that is, I think, how much is the population of Japan compared to India? I don't even know. Japan is about 133 million. India is about the same 1.4 billion or thereabouts. So they're about 1% of us. 10% of us. So at 10% of us, they have remained world leaders in economy since the 60s. And what happened in the 60s? The high-speed rail was developed. So yes, the productivity of that cluster. Thank you. That is the exact correct answer. Now, again, when we talk about high-speed rail, I'm going to talk more about the Japanese model, of course. But when we talk about high-speed rail, I want to emphasize that high-speed rail has many different development paths. It has many, many different paradigms of design, environmental control, operation, development. It has many, many different paradigms, even of things like maintenance, renewal, ticketing, signaling. Signaling is actually part of operation. It has a different fare and revenue structure, and certainly a completely different life cycle in every different part of the world. So for example, if you go to Europe, European high-speed rail and Japanese high-speed rail do not mix. Their standards are different. Again, we'll cover that later. Their standards are different. Apart from that, the project execution at the planning and capital stage, the project execution is also completely different. So, for example, if you go to Vietnam, Vietnam's high-speed rail is following a different trajectory than either Japan or India. And China is on a different track altogether because China's high-speed rail technology is more or less indigenous. So, the development of HSR or the development of any kind of, not just the development, the design and development of HSR would be vastly different based upon the prevailing norms. And those prevailing norms are generally geopolitical and geosocial and geoeconomic considerations. Now, that does not change the one fact. That does not change one immutable, intransmutable fact, which is that a high-speed rail is a highly, highly, highly capital-intensive enterprise. Can anybody here define a mega project for me? I've used a word here in red, which is called a mega project, because all high-speed rail projects, all high-speed rail enterprises throughout the world are mega projects, without exception. So can anybody define what a mega project is?
Much investment is there.
Yeah, much investment is there. How much investment? Much investment, that is one point, and it also has a second, it also has a second aspect. You are right. Beg your pardon? Infrastructure is much bigger. Yes. Okay.
Sir, in Indian context, these projects cannot be funded by Indian banks.
Yes. Okay. Yes.
They don't have that capital.
Yes, I agree. That is a very good way of thinking about it. That's something that for which we need foreign funding, or something for which we need extra national funding. Yes. Okay. In fact, it cannot even be funded by the Indian Treasury. Consolidated Fund of India doesn't have that much money to spare for one project.
Level of production is very much level of investment in terms of human resource.
Yes, exactly. The level of investment in terms of human resource. Now, all of you have talked 1, 2, 3, 4. 4 people have just now talked about the investment side of the equation. What about the return side?
Time to complete.
Time to complete the project, what about? Less or more?
More time.
More time to complete the project? Not so much. Sorry. Employment. Yes, that's one of the dividends that we reap from a mega project. What other dividends can we reap from a mega project? I would like to remind you, I'd like to call you back to what, I'm sorry, I forget your name.
Sir,
Nitish. I would like to call you back to what Nitish just said a few minutes ago about the productivity of the cluster. When we talk about a mega project, we are talking about, we are talking about a project that is in the neighborhood of $1 billion plus for a single project, right? A single project, and its branch lines or the projects that or the ancillary projects that branch out from the main focus will have different capital outlays altogether. So, just the main project, which in this case, in the case of high-speed rail, is just the track and rolling stock, nothing else, will be about in the neighborhood of $1 billion plus, which, as Nitish just said, is the amount of money that you need to is the scale of investment that you need to start sourcing from foreign banks or from the IMF. And it has and of course the design considerations are huge. And once it is executed, then we hope to achieve a recovery, or we hope to achieve a recoupment on our investment that is much larger than we would directly compute in a certain rate of return. It is much larger than a standard 6% or 10% or 20%. We hope to achieve a recoupment on our investment that is that in terms of far-reaching socio-economic impacts, which would be exactly what Nitish said about the productivity of the cluster. We hope to take ourselves into a new economic cycle by means of a mega project. That is a mega project. $1 billion is not a mega project. Far-reaching socio-economic implications is not a mega project. New design is not a mega project. When you put all that together, that is what we get. And why am I emphasizing on this word so much? I'm emphasizing on this word because because as far as mega projects are concerned, there is a single, how shall I say, a single entity or a single, there is no single entity or no single agency that can execute it. Therefore, it must always be executed by a conglomerate, which is why it involves an enormous amount of coordination, nationally as well as internationally. And that's why a mega project, for example, and that's why, just to put it in perspective, the railways till now has never executed a mega project before them and the High Speed Rail. I'm talking about the railways proper. Metro is a separate argument, and yes, I agree the metro would fall in the region of a mega project, although I'm not quite sure what the budget of the metro would be. And technologically, as well as from the point of view of just pure business, the high-speed rail is one of the fastest growing sectors in railway technology today. What do we mean by one of the fastest growing sectors? We mean that it is the kind of, that the whole of railway technology on the one hand is in a state of stasis, is in a state of stagnation, is in a state of basically of decline, because the technology is getting old very quickly and is being very rapidly outpaced by new developments in aircraft and roads. Except high-speed rail. So that is one of the main reasons why we talk about high-speed rail. We know that it is the next big thing, and it has remained the next big thing for the last 20 years, and it is likely to remain the next big thing for the rest of this century. Which means that anybody who wants to remain in business in the railways today, any company, any professional, any consultant, any engineer who wants to remain in business in the railways today without the benefit of a government job, needs to know how to work with high-speed rail. So, what is high-speed rail now? We talked about the why. Now let's talk about the what. This is a lot of technical jargon that I have included on the slide. But basically, can anybody tell me what is high-speed rail? There's a very general kind of when you say high-speed rail, or when you hear on the news the word bullet train, what does it conjure? What comes up in your mind? What image does it bring up?
Speed.
Yes?
Speed.
Second part? Speed.
Yeah.
Okay. How much?
More than, I think, 250 kmph.
More than 250 kmph. Okay. That's correct. That's one thing. Yes, absolutely. And I think you were saying something. I think somebody here was saying something.
Acceleration.
Acceleration. Acceleration.
Yes, sir.
Yeah. Okay. Fine. We're talking about distributed power. Yes. We will have to talk about acceleration, especially rapid acceleration.
Rapid.
Yes. Okay. Agreed. And
Better synchronization in different systems,
better synchronization in between different systems.
like braking and acceleration and
TCM.
more systems.
Yes, exactly. Yes, okay.
TCM.
An intelligent system that basically functions as an integrated unit.
Yes.
Absolutely. Yes. And
Design. Isn't it design is different from other trains?
the design is of course
Comfort.
different from other trains, but I mean, like, what do we mean when we say different designs from other trains? Are you talking about the shell,
Comfort.
the shape?
Comfort.
Comfort levels.
Comfort is-
Shape is entirely different to meet the
Yes.
requirements for high velocity, high speed.
Yes.
Comforts.
Okay, fine. The shape is, yes, that is actually when we talk about a bullet train, we always think about a train shaped like a bullet. I think that's what I think about. Okay, fine, correct. Yes.
Automation or less human interference for operation of the train.
I'm sorry, you used automation or optimization?
Automation.
Automation.
Yes.
Okay, fine. Yes, okay, agreed. All of this is absolutely correct. So basically, the way, and all of you have a correct impression. But basically, the way the UIC, the International Union of Railways in France and Belgium, UIC Paris defines high-speed rail as a grounded, guided, low-grip transport system. Now, that is a very, very fancy way of saying train, which is basically, well, why do we say grounded? It's grounded because because a plane cannot become a high-speed rail. It's guided because a car, which is not guided, it just runs on the road by a completely different mechanism, it's guided, and therefore a car cannot be high-speed rail. It has to be run on a rail, and it's low grip. Can anybody tell me? Let's talk a little bit about this word, about low grip. Can anybody tell me something about it? When we say low grip, what do we mean, and why have we defined low grip over here? Acceleration. Less friction. Okay, fine. That's one way of looking at it. Metal to metal contact. Agreed. Okay.
No slip.
More slip.
No slip. Zero slip.
Okay. Okay, fine. Okay, all of that is correct. Basically, the idea of low grip is all that you are saying. Plus, it is also the idea that when we talk about high speed, we're not talking about starting torques and starting power. We are basically yesterday we sat right here and we talked about tractive effort, and about tractive effort at starting is higher than the tractive effort later on, and how at the higher speed the tractive effort that we require is less. So basically, we want speeds in the neighborhood such that the tractive effort required is less, and it is not hampered by, as somebody said, friction, and that is why we need a low grip transport system. Now, by this definition, does anybody think that maglev would be high-speed rail? Everybody understands maglev, right? Magnetic levitation. Yeah. So, how many of you feel, according to this definition, by that maglev would be high-speed rail? It would be. Okay. Can you explain why?
No contact chain has very runs high speed.
Okay.
Grounded, guided.
That's exactly my point. How is maglev grounded? It is literally magnetic levitation. How is it grounded?
Only guided.
Guided, yes, okay. Yes, it is guided.
No ground.
It is.
So its threads are elevated, are
Not ground.
not properly.
Exactly.
Its threads are elevated from the ground level.
Not in touch with.
No, the track is elevated, but the train is also elevated.
It is not grounded.
Exactly, it's not grounded.
How can you say low to?
I mean, just an interesting thought experiment. I have not yet come to any kind of satisfactory conclusion as to whether I would call maglev high-speed rail by this definition. Broadly, generally in the world, in most high-speed rail societies and conferences, maglev is considered a legitimate component of the high-speed rail pantheon. It is in fact called high-speed rail. It is called a branch of high-speed rail and not a new technology altogether. Okay. Now, everybody here just basically outlined the other points that are on the slide. So when we're talking about speed, we are talking about speed in excess of 200 kilometers per hour, as you mentioned. We're talking about a combination of several infrastructural elements. We're talking about a certain number of railway standards. Now, I'll discuss standards a little while later, but right here at the bottom of the slide, I've written a few words: interoperability, high capacity, safety, sustainability. So, in each particular railway system, we have certain design paradigms, we have certain implementation methods to achieve our goal, and we have certain local, technical, as well as geoeconomic and geosocial considerations, on the basis of which different countries have achieved a different developmental path to get to the high-speed rail. We've already discussed that. But some of the things that remain constant, or some of the things that remain uniform across high-speed rail, across all components of high-speed rail, and across all systems of high-speed rail standards, which we shall discuss, is this bedrock. So, which is why I must outline it before I proceed. So, we have interoperability. The idea is that a company's standards should not be so specific, and I'm using the word company here loosely. It could be a nation, it could be a national government, it could be something like the Indian Railways, which is a government department. But a system should not be so specific and so specialized as to become monopolistic. Does that make sense? अगर हिताची का आपने कोच ले ली, हिताची का आपने ट्रेन सेट खरीद लिया, then you have to use Hitachi signaling systems, Hitachi Panto, Hitachi Track, Hitachi this, Hitachi that, and then you get locked into that entire system and you cannot change out. That is something that all railway societies, including the International Union of Railways, is extremely strictly against. Which is why all high-speed rail systems must have a certain degree of interoperability. The rest, I think, is more or less self-explanatory. You have high capacity, you have safety and security, because of course no system is useful unless it's safe, and of course no system is useful unless it carries the capacity, it has the capacity to carry enough people to pay for it. So there's that. Now, yeah. Okay. So when we talk about the history of high-speed rail, on these parameters or on these lines, we know that the first high-speed rail in the world was invented. I will use the word invented. Was invented and designed by the Japanese, by the then Japanese National Railway, the JNR, which was at that time a government department like the railways before it was privatized entirely and split into 7 different private companies in 1987. So in 1964, in preparation for the then Tokyo Olympics, non-pandemic, non-corona Tokyo Olympics, in 1964, basically on the 1st of October, this, which was actually a little bit later than planned, we got the Tokaido Shinkansen. And that is the point at which high-speed rail, the point at which the history of high-speed rail begins. And we can see that we have various different lines or various different lines of development that we in various different parts of the world. So, for example, high-speed rail did not actually catch on until the early 80s. Actually, the late 70s, early 80s in the rest of the developed world, basically in Europe. So, for example, the first high-speed rail line in Europe was all the way much later than 64. It was all the way 14, 15 years later in Italy. And then immediately after that, in the next decade or so, it caught on. And these days, when we think of high-speed rail, we think of Europe. And China has a different chapter altogether. China's history of high-speed rail used to be one very short metro line from the center of Shanghai city to the outskirts of Shanghai, which was about 15-16 kilometers, and which was a distance that could cover in about 5 to 7 minutes. And that monorail, sorry, it was not a monorail. That urban rail transport system, that single line, was the whole history of high-speed rail in China until 2003. And I'd just like to draw your attention to the Asia line. And notice that there is a slight bump when China starts building, and then there is another bump when China takes off, and then that graph, that's all China. And look at the total graph. The total graph is also basically in parallel with this. So when we talk about the development of high-speed rail today, we talk about the Chinese model, for better or for worse. And just to hammer home that point, let me take a look at this particular graph. This is the distribution of high-speed rail length. The high-speed rail kilometer length. That's to say, route kilometers in different countries. And this is just taken from a research paper. But I'd just like to show you the market share. Just look, we have China, which started building its railways not even 20 years ago. We have China with nearly 2/3 of the HSR market by passenger, PKM basically. And we have China with not just the vastly the vastly larger lines in operation, but also the largest margin by far of ongoing projects. as we speak. So the reason for that, of course, is something we will discuss later. But when we talk about high-speed rail today, we think about Europe, but we talk about China. And I'd just like to point out here that this is something, I mean, notice that each line of high-speed rail that China is executing is a mega project. We are talking about one single Mumbai Ahmedabad high-speed rail corridor. So when we talk about high-speed rail, I will not talk about developmental paradigms here, but what I will try to emphasize here is that what we are competing with is there. It is not there anymore. It's no longer Germany, Sweden, and the UK. So again, one more thing that I would like to point out here that it is not possible in any democratic country to do what China does, and I would not like to see it being done on a very personal note. But that does not change the fact that that's our country. I have not included data about Vietnam's model, about the Thai model, about the new MMRTC in Singapore. I've not included data about for example, the Danish model, which is completely different, or about Taiwan's TOT of back in 2007. I'm not including any of that data for the simple reason that it is not very freely available. And again, that is no longer the focus of our attention. So, again, harp on the Chinese model a little bit. That is high-speed rail in China. As of, I think, 2016, if I'm not wrong, when is this graph? Yeah, 2016. And just to put it into perspective, 15 years before this, in 2001, the Chinese high-speed rail would have been, can you see Shanghai right here? I'm not sure if it's very clear. That's Shanghai. And from Shanghai, right here. Not reaching the next dot, about halfway to the next dot. That would have been the history of Chinese high-speed rail in 2001. This is the map in 2016. Again, why high-speed rail? Why is China so interested in high-speed rail? Why are their ambitions are very clear to the rest of the world, but then why is it that high-speed rail is the way in which they want to achieve that ambition? Because the United States doesn't have high-speed rail. In fact, in the US, the US's high-speed roadway network would look pretty much similar to this in density and in quality. So why is China so interested in using high-speed rail specifically?
Simplest means of transport.
We are talking about China, right? We are talking about that China in which, okay, fine. Safest means of transport is one way of looking at it. Fine.
Sir, China has a much higher population than US, so roughly they are same size, but population of China is much higher than US.
Agreed.
So mass transportation is more required for China than for US.
That is agreed. But I would like to remind you that back when this was being conceived, the population of the population of China was a waning consideration. So while you are correct, I would like to hear just a little bit more from somebody. Somebody was saying something.
Cost of passenger carrying per kilometer is lesser than any other means of transportation.
Okay, absolutely agreed.
The China is a very large country.
Yes.
Geographically, cities are very apart, very long distance.
Yes.
So they need high speed to lower the traveling time. So that's why rail network, as it is cost effective. So they have advantage of laying more and more rail network.
Okay, I agree.
To transport army and arms very quickly.
Who said that? Thank you. Exactly what I said. We're talking about territorial integration. And territorial integration from a strategic especially from a military standpoint, is not done generally by road. That model is outdated. 2000 years ago, the Romans did it. But after that, we need the rail. The British did the same in India, by the way. When the British came to India, there was no rail in India. Obviously, the technology didn't exist at the time. When they left, the British had built something like 54,000 route kilometers in India. Today, we have something like 64,000 route kilometers. Right? The reason for that is not, the British were not interested in the welfare of Indians. We may be speaking their language, but they were not interested in the welfare of Indians. What they were interested in was this: strategic importance. And let's hark back a couple of slides to what I said earlier. High-speed rail is the burgeoning sector of the rail, is the burgeoning component of the rail sector. It is the one component of rail that is not going down. And so we have technological competitiveness with the rest of the world. And the rest of the world in this case is not the US. As somebody pointed out, the US's, I think Nitish, it was you, the US's, the US requirement is completely different from the Chinese requirement, and it's completely different even from the European requirement. Mainly because in China, as in Europe, in fact as in India, we need to connect urban centers for for mobility, then for commercial purposes. The US has taken it the other way around. And in any case, the US historically has suffered from certain very powerful vested interests that forced government investment and government intervention in the roadway sector and stalled all possible rail projects. So that's again a very interesting case study that I would recommend all of you to Google and read if you have time. Okay, so we have, and of course we have the economic impact, we have the quality of life, we have all of those concerns. Plus one concern that I don't think anybody here mentioned, which is environmental sustainability. Somebody mentioned that the cost per passenger or cost per PKM is minimum. But when we say cost, we don't just mean the environmental, we don't just mean the economic cost, we also mean the environmental cost, which is also minimum in China. And which is why today China can actually afford to commit to to reduction of greenhouse gas emissions, because they have a high-speed rail network that can allow them to move their people without relying as much as many other countries of an equivalent size would do. I'm not talking about India on environmental sustainability. So, but the main topic that I wanted to discuss today with you on this point is something called the spillover effect of high-speed rail. If any of you has not Googled it, I would really highly recommend you to write this word down and Google it. The spillover effect of high-speed rail. Please Google it. You will find lots and lots of information. You will find lots and lots of research papers. Please don't bother with the research papers. But I have linked this article here. It is a very recent article, just last month, published by the ADBI Journal on its blog page. It's a very, very interesting article about the spillover effect of high-speed rail. And the spillover effect of high-speed rail is easily seen in a place like Japan. This is what Japan used to be. This is what Shibuya used to be. Is anybody here familiar with Tokyo? Anybody interested in anime or anything of that sort? Because Shibuya crossing, this is what it looks like today. It is in fact the largest crossing in the world, with which is basically a six-way crossing, 1, 2, and then around the diagonal. And every 300 seconds, that's every 5 minutes, I think, the equivalent of a total of, I think, about 1,000 people cross the street on this crossing each every 5 minutes in total. And that tells you about the kind of activity, and you can see what it is. And this is what it used to be a few short years ago, before high-speed rail reached Shibuya Junction. So, so when we talk about high-speed rail, we're talking about basically the spillover effect of high-speed rail. Spillover effect of high-speed rail, as Nitish pointed out at the beginning of this lecture, is the enhancement of productivity of that particular cluster of cities. We're not talking about one city, we're not talking about two cities. The Tokaido Shinkansen, for example, was built to operate between Tokyo and Osaka the two large urban hubs, passing through Nagoya, which is smack in the middle of Honshu, and which was a very important burgeoning cultural center at that time. Now it is both a cultural and an economic center, with at least I think 3 other cities on each side, 3 other major urban centers on each side. But when you're talking about megacities and metropolises, we're talking about Tokyo on one side, Osaka on the other, Nagoya. That was the Tokai District. And just that one Shinkansen was enough to propel Japan onto the world stage, with the result that in about 15 years it was beating the United States at a time when the United States was a far more resilient and resurgent power than it is deemed to be today. And this is the kind of transition it produces, not in 50 years. This is the kind of transition it has produced in barely 20 years, because Shibuya has not changed in the last 20 years. So we are not talking about development at a point. We're talking about a development ecosystem, which is the movement of people, and more specifically, democratizing the movement of people. So again, please read that article and then come back and talk. So let's talk now about the Indian case, or about the Indian high-speed rail equation, which is quite fraught, but basically we are importing our technology from Japan. We're importing the E5 series Shinkansen from GR East, to be more specific. We are operating it on a G2G model, on a government-to-government model. We are employing Japanese contractors and Indian vendors, Japanese vendors and Indian contractors, my bad, in order to execute the project on the ground. And we hoped back when it started in 2016, we hoped to be able to start the project to start operations in 2023, but in 2021. But now the date has been pushed further to 2023, and it will likely be pushed even further beyond that, because of delays due to Corona, delays due to various other problems that are associated with the mega project. Needless to say, the project has generated considerable excitement. If any of you has the time, please go back and read the research paper, the IIT Madras research paper on the mega project. Now, when we talk about the execution of high-speed rail on the ground, and this is the problem across the board, by the way. When we talk about the execution of high-speed rail on the ground, I mean, you have the slide in front of you. But what do you think would be the major challenges or the major difficulties that would arise?
Land acquisition.
Beg your pardon?
Land acquisition.
Land acquisition, okay. And?
Building the infrastructure.
Beg your pardon?
Infrastructure building.
Infrastructure, okay. You have the slide in front of you, as I said. Okay, so the land acquisition is, of course, the most important and the most crucial aspect of the project. And in fact, to the extent that most vendors, foreign as well as Indian, especially foreign, will give you a date of completion of so many years or so many months after land acquisition. That is the way in which all dates are decided. So land purchase is, of course, a very, very significant problem for all of us. Whoever wants to build a high-speed rail corridor on their turf, whether it is Japan, whether it is Vietnam, whether it is China, whether it is India, whether it is Europe. Now, different parts of the world have solved that problem in different ways. One of the reasons China is so advanced on high-speed rail is because they don't need to worry about land acquisition, right? As I said, I would not like to see that model replicated in India. It is not a model by which any democratic country can hope to develop. And thank God for that, as far as I'm concerned. But be that as it may, Japan solved the problem of high-speed rail in a very interesting way. It did it by the means of the land trust schemes. the land, and this is important to know because if high-speed rail is to be popularized in India, we might well see a similar model operating here in India. So what's the land trust scheme? The land trust scheme is basically the idea that the land is acquired for use through a trust bank, and the owners of that land, instead of having to sell it, will earn an income from it in the form of a government bond. So this is something that became very popular in Japan, and for which many people were more than willing to pick up their land, because land which was at that time for them a relatively low value asset, would suddenly become a very high value asset, and they would stand to gain from the project in perpetuity. While they themselves could leave that land and come to the urban centers to work and have a thriving lifestyle in a burgeoning metropolis. That is basically burgeoning because of high-speed rail. So that is the Japanese model. The Indian model is somewhere between the two. The Indian government's technique of acquiring land is pretty well documented, and it is as we would do for any other land-based project. Now, there's a word on the slide which is viaducts. The land acquisition, basically for high-speed rail, you can build the track on the ground. You can build the track on an elevated overbridge system, as you can see over here. And this method reduces the land you would need by about 1/3. So basically, if you needed 100 square kilometers of land earlier, you now need about 66 and odd square kilometers, which is a huge reduction, and which is the method that India has adopted for building its high-speed rail across most of the stretch. So, and you can see over here the viaduct being laid. It is being laid in the form of these prefabricated concrete blocks and which will be put in place on these pillars and jointed, and then the rail can be laid on top. So, whenever we talk about infrastructure for a high-speed rail project, or whenever we talk about infrastructure for a rail project, we must always consider these some important points that will then become set in stone, quite literally set in stone throughout the duration. Whether we have dedicated or mixed traffic, whether we have a ballasted or a ballastless slab track. Can anybody tell me what kind of track we have on a high-speed rail in India? Ballastless, yes. Why do we have ballastless? Any idea? Okay. But then that problem will be everywhere. But Japan has some ballasted and some ballastless tracks. Why is ballastless track being chosen by India?
Sir, we are building these kind of viaducts, so it won't be feasible to have ballasted tracks.
Excellent. That's one reason. And there are two reasons. That is one reason. There is a second reason.
Environmental effect.
Thank you. So that is the reason why in most places the ballastless track is what we are looking at. Another reason is actually also that which actually ties into your point about the viaduct, which is that the ballastless track will be more conducive to drainage of water in a high rainfall area. So that's also one reason. Now, when I talked about interoperability a few minutes ago. The interoperability of the gauge, the interoperability of maintenance patterns, the interoperability of signaling systems, and the interoperability of all control circuits. That is what we're looking at. This is something that you can read on your own. But basically, the idea is that when we frame the technical specifications for a high-speed rail project, we frame it in totality, right? We frame it for the track, the rolling stock, the panto, and the signaling together, and the operational control systems, whatever the RAM system will be. because whatever operational control, whatever computerized operational control we will have a RAM system. And the system will have to be such that it can cater to a change in rolling stock or a change in signaling system if needed. As sir was saying this morning, आज आपके fitter ने Alstom सीख लिया, कल को Bombardier आ गया तो कैसे करेगा? परसों Hitachi आ गया तो कैसे करेगा? Because all the systems will have to have some amount of basic interoperability or some amount of basic standards, and that is what brings us to basically the meat of today's lecture, which is the technical specifications. So these are the technical specifications for Shinkansen rolling. Oh, sorry, these are the technical specifications for design and operation and maintenance of high-speed rail rolling stock. These are basically the considerations that we will have for high-speed rail rolling stock. Time कितना बचा है?
12:45. 12:45, sir.
12:45. Okay. So we have about 45 minutes until lunch. And we are now entering the technical part of the presentation. Until now it was all pretty general. So would you like to take a 5-minute break and then come back? Okay. Right, we have a 5-minute break.
इसका दूसरा कारण क्या बताया था? किसने बताया था? हाँ? बड़ी तेज स्पीड संडे को हाँ एकदम
Are you all back?
Yes.
Okay, thank you. So, everybody's refreshed? Shall we start again?
Yes, sir.
Thank you. बीच में मुझे करीब जब सवा एक बज जाए तो मुझे बता दीजिएगा, ठीक है? तो अगर मैं भूल जाऊँ, हालांकि मैंने लैपटॉप सामने खोल लिया था कुछ टाइम में, सवा एक बज जाए तो मुझे एक बार बता दीजिए. I will not start wrapping it. So, technical considerations of high-speed rail rolling stock, or technical considerations of any rolling stock that we hope to run on high-speed rail. These are, okay, this is basically taken from a seminar conducted by about the Mumbai-Ahmedabad project. So it is basically a seminar conducted by NHSRCL, JR East, ADBI, and RTFI together. And therefore, these considerations are those considerations, or these technical specs are those specific technical specs for which we in India are most concerned. Believe you me, there are many more, right? So, first and foremost, one of the first considerations we have is what kind of train do we want? Remember, we have now decided our track. We have decided our mode of passenger traffic, right? Which is going to be passenger and not multimodal, not mixed. We have decided how fast we want to run our train. We have decided therefore our route. Now, what kind of train do we want? Does anybody know the meaning of this word? Articulated versus non-articulated rolling stock.
Connectivity between bogie and coach.
Connectivity between bogie and coach. Yes, exactly. Sorry, where you were?
Sir?
You are from
ICF.
ICF. Thank you. No matter. Okay, so we have articulated versus non-articulated. The train 18 is articulated or non-articulated?
It is articulated.
It is articulated, right? Why? What are the benefits of articulated versus non-articulated coach or bogie design? Can anybody tell me? You of course can, but yes.
The sway will be less.
Sway will be less. Yeah. Okay. And
Better riding index.
better ride index. Yes. And all that you, yes, it's absolutely correct. But why do we use an articulated bogie?
No vibrations.
Right index. Okay.
Easily negotiate curves.
Thank you. Yes, easily negotiate a curve. So when we talk about an articulated, okay, can anybody tell me the name of a very famous articulated rolling stock coaching system that came to India a couple of years ago? Not LHB.
Retro.
Talgo. Yes. Who said Talgo? Thank you. Yes. Somebody here also said Talgo. Yes, Talgo. LHB is not articulated by the way. So we are talking about. So why do we consider it? We consider it because we need a train that can navigate a curve at high speed with low vibration and no change in ride index. So if you were to take a look, this is what an articulated train looks like. This is one coach, this is the second coach, this is the vestibule in the middle, and in the middle we have one single bogie that is fixed like this. Is this clear? This is basically the design of an articulated bogie. And of course, when you have a coupler in the middle, which is relatively rigid, especially for LHB, and you have separate bogies for separate coaches, then what you get is, of course, a detachable coach. If you want tomorrow, then suppose this is LHB, then tomorrow this LHB coach can be detached and a new one can be put in its place. It's no problem, which is the benefit of an articulated system. But an articulated system is because it's a train set effort to integrate it. There is no way to detach this coach and keep this bogie functioning. But it also means that first and foremost, if you were to look at our coach like a beam, then the articulated system would of course give you a lower center of gravity and a much better stability. Also, if you were to look at the if you were to take a look at the brake pads, sorry, not at the suspension pads, the coach, is it clear? I'm sorry, I'm standing in your way, I think. Take a look at the suspension pads. One on one coach, one on the other coach. What is the benefit of that? The benefit of that is basically that when our train navigates a curve, not only do successive wheel sets get to tilt with respect to each other, But because those wheel sets are mounted on separate coaches, the whole coaching system gets to tilt with respect to the other, and the train navigates its curve at a very, very in a very, very stable manner at a much higher speed than it otherwise would be possible. So that's the articulating system.
Sir, how the bogie connected to the coach body and both the coach bodies are connected in that articulation?
The bogie is connected to the coach, like
Body.
whatever the suspension system is,
Why the suspension?
whatever our suspension system is over here, whatever spring mounted or air spring mounted or dashboard mounted, whatever suspension system we are using, there's the same suspension system that we're using for the articulated one as well. The two are independent.
Sir, coupler
इसमें I don't think coupler है because bogie है आपके पास and एक lateral suspension system आपको दिख रहा है, primary और एक secondary. Then we have aerodynamic profile. Excuse me. All of us again. So when we talk about aerodynamic profiles, this is of course one of the most famous aspects of the bullet train, right? Whenever we think about a bullet train, somebody mentioned that they think about the profile, which is of course that's where the name comes from, bullet train. So, but what people don't really understand, or what people don't appreciate, is the fact that the profile itself is not a single design. Sir talked about this morning about the design of the nose cone, which is separate from the design of the rest of the train onto which it is mounted. But also, the aerodynamic profile will have to depend upon your own considerations, what your own environmental considerations, what terrain you are operating in, or what kind of environment in what kind of environment you wish to run your train. So the aerodynamic profile in this case is basically a function of your navigational requirements. So let's take a look at, so we have this is the Shinkansen N700. This is a photograph that I copied this morning from CNN. So your E5 will look slightly different, but look at the nose cone. Look at the nose cone, just how long it is compared to a single coach. Right? The E5 is even longer. And also notice the topology of the nose cone. The topology of the nose cone is not rounded, it is rather flat on the top. Right? The Japanese call this tsumame, which is tsumame is the Japanese word for swallow, the swallow bird, and its beak, the lower part of its beak is shaped like this. If you look at older Japanese rolling stock, older models of the Shinkansen in the 80s, for example, or just Google the image of the first Shinkansen. You will see an almost circular conical kind of nose cone, where this nose is in the center. So the aerodynamic standard is completely different based upon what you want. Now, if you take a look at has anybody ever Googled images, or have you ever seen images, or have you ever seen European high-speed rail rolling stock? The European TGV or anything. I see. Okay. So its nose cone is different. Its design, aerodynamic design, is also different, and yet it gives equivalent or better aerodynamic performance by their standards, because they are operating in the hilly regions of France, and also they want to expand into the plains in Eastern Europe. So the aerodynamic profile is basically now the one of the most important standards for high-speed rolling stock is the EN 14067 standard, because that dictates the aerodynamic profile. That dictates the way in which your rolling stock should. That dictates basically the air drag requirements or the air drag coefficients which your rolling stock should achieve. The EN 14067. It is a French standard basically, it's been given EN because it is now an EU standard adopted by the International Union of Railways, but basically it remains a French standard. Then we come to tilting trains. Again, navigate a curve. Why do we need a tilting train when we have an articulated bogie? Yes, an articulated bogie also helps you negotiate a curve at high speed. So why do we need a tilting train in addition to an articulated bogie?
Keep the coach body perfectly horizontal while negotiating curve.
To keep the coach body perpendicular to the...
Perfectly horizontal.
Okay, right, yes, correct. Basically to ensure right angles.
To avoid tilting.
Exactly, to avoid tilting and to ensure right angles, to ensure right comfort, to ensure right stability. Technically, this becomes. I mean, the idea of a tilting train is basically a function of a suspension system. So let's take a look at that. Again, I wish I had been able to organize the slides in a slightly different way, but this is the tilting. This is the tilting train system of of the Shinkansen rolling stock. And the unique feature of this is that it is not just useful on a banked track, on a curve. It is also useful for earthquake protection. Because, as we all know, Japan is one of the countries that receives the maximum number of earthquakes in a year. Japan is in fact so seismically active that people are now thinking of when the next big earthquake will strike. Right? 2011 was Fukushima. It's now 2021. People are worried that a new earthquake should come quickly, because if it doesn't come, then the next one will be even worse. So, the Japanese have learned to live with the earthquake. They have learned to tame the earthquake. This is one of the means by which they've done it. Now, this is something that I've copied and pasted here directly from a Japanese slide, basically from a slide at a seminar of GR East. So, which is why all of you can be forgiven for not reading it, for not being able to read it, which is fine. But I will just try to explain it to you once, just to give you a very, very short exposition. We have, how do I say it? Can everybody see this particular dashboard over here? Basically this one. The idea is that when the train tilts, then then we have a horizontal and a vertical damping system, hydraulic damping. Sorry, damping system that is basically used to ensure that the tilt, once it happens, is nullified pretty quickly, and the vibrations resulting from that tilt are also nullified pretty quickly. And this means, as of today, the Japanese rolling stock has a unique advantage in its earthquake protection, has a unique advantage over all other high-speed rail rolling stock systems available in the world today. That's one of the reasons why they were the ones that were tapped for MHSR. We go back. Pressure comfort. Can anybody tell me what this is? Because this is not something that we're used to hearing about in the railways. This is more of an aircraft concept. Pressure comfort. Yes?
Pressure loss due to high speed.
Okay. Okay.
Related to G forces.
No, thank you. Sorry. When we talk about pressure comfort, why do we talk about pressure comfort? Again, a unique aspect of high-speed rail. A unique aspect of high-speed rail, not limited to the Japanese Shinkansen. It is a unique aspect anywhere where speeds cross something like 190 to 200 kmph. It is a unique aspect in which in order to prevent as sir mentioned, in order to prevent the drop in air pressure within the cabin due to the high speed, the entire cabin, the entire coach is hermetically sealed and pressurized like an aircraft. In fact, it is the exact same criteria that we use in an aircraft. And so when we talk about pressure comfort, we talk about a design consideration for passenger safety. And in that respect, therefore, this particular criteria, the pressure comfort criteria, is an extremely strict criteria in which the air leakage, that is to say the drop in air pressure due to leakage, should be at no point more than 1 kilopascal per second. This is also very, very high. This is basically 1 kilopascal per second is the amount that is permissible for some medium speed rolling stock in Europe. The Japanese standard is 0.2. So again, a unique characteristic of high-speed rail that we're completely not used to talking about in the railways. Ride index, everybody knows what ride index is, right?
Sir, what does it mean by KPA?
Kilopascal. Kilopascals. So it's drop in air pressure, right? Ride index. Everybody knows what is ride index, right? Can anybody tell me what is the ride index of a Shinkansen coach? Approximately. Okay, what's the ride index of an ICF coach? 3.2. What's the ride index of an LH? 2.7. सबको प्रवेश कराता हुआ है. उसके बाद, what is the ride index of a Shinkansen? Maybe 2. Okay.
Less than 2.
You tell me here. Huh? You're correct. It's about 1.8. Something between 1.8. Efforts were made to reduce it still further. The N700 has a ride index of is rumored to have a ride index of something like 1.4, 1.5. But that is a very ideal case, and that is not something that has been verified in any publicly available research. I'm sure RTRI and GREs have done their own work, but I am not privy to any of that information. So that's ride index. Anybody knows what exactly is the ride index? How do we calculate it? Just out of curiosity. No, okay, that's fine. That's I agree, but that's the practical aspect.
Sir, I have heard the formula.
Sir. It is. That's why I was asking if anybody has heard it from RDS, so then I would really love to know what the formula is. Because I once looked at the formula, it is basically the 10th root of the product of the root mean square amplitudes of the vibrations in each of the 6 major cardinal inflections. So, so the idea is therefore that it should take into account the ride comfort due to all the 3 translational and all the 3 rotational planes of vibration. 6 degrees between all right. So that's right index. Just a bit of trivia. Don't worry. Then we have noise and boom. Okay, this is something that's very interesting. Okay. Okay. Can anybody tell me about something about the noise criteria for high-speed rail? What exactly are we afraid of when we say noise? Yes?
Volume of
Air? What?
Volume of air is expelled sideways.
Gives noise, yes. Okay.
You are breaking the column of air.
Okay, yes. You're breaking the column of air, but you're still breaking the column of air with a normal running train. You're breaking the column of air in a car. Why are we worried about a sonic boom in a high-speed train?
For vicinity area, residing people, vicinity area, for discomfort, so that they may not get disturbed.
I mean, yes, I agree. That's the broader aspect. Mainly the idea is that a high-speed rail traveling in excess of 320 kmph will be breaking the sound barrier. even if it is traveling at 250 kmph, even if it is traveling below max speed, it will still be, as somebody mentioned, breaking a column of air, and that column and the column of air that it will be breaking will be absolutely not a problem in the plains, but it will be a huge problem. Yes.
But in tunnel it is
Exactly, in a tunnel. Now I wish I could share with you the graphic from NHSRCL about the high pressure dome that is formed ahead of high speed rail coach and ahead of the high speed rail nose cone, and on each side of the nose cone you have a low pressure dome, and that is the transfer of energy that results in a sonic boom. But basically the idea is that a sonic boom is generated, and that sonic boom can be measured in decibels. So, in fact, let me go back to aerodynamics, because this again ties back to aerodynamics. The standard is again the EN 14067, which specifies that the maximum amplitude of the noise that is generated will be used as our standard. That will be minimized. What we will minimize is the maximum amplitude. Right? You have a wave, and you want to keep the highest peak of that wave below a certain level. That's the European standard. How do the Japanese look at it? The Japanese measure the peak-to-peak amplitude averaged over the entire duration of the boom, and by a weighted average RMS method, and that weighted average must be less than the criteria. So the Japanese standard, as we see, is much stricter than the European standard. In fact, one of the major incompatibilities between rolling stock produced in Japan and in Europe is the sonic boom factor, because the Japanese have a much stricter criteria for that. Especially, and why do the Japanese have such a strict criteria for sonic boom?
The train is running mostly in tunnel.
Thank you. Exactly. The train is running mostly in tunnel, and the biggest sonic boom is produced at the entrance of the tunnel and at the exit of the tunnel. And Japan is highly dense, and Japan's population is dense enough for people living in the vicinity of the tunnel to be extremely inconvenienced. In fact, life becomes unlivable. Unless you have the characteristic Japanese nose cone, because the Tsubame does not produce very much more noise than is normal. And suddenly, you have people in the vicinity living in the vicinity of a high-speed train, whose life proceeds completely normally, even with the train passing next door at 320 kmph. One of the requirements of our sonic boom, one of the requirements for aerodynamic design in order to minimize sonic boom is something called the TF, or the train shape factor. And the train shape factor is basically a number that is basically as a number it is a very important component of the formula, and I will not get into a detailed discussion of that here. But suffice it to say that the train shape factor is basically different for different nose cone designs, and therefore it is different for European and Japanese rolling stock, and in fact it is one of the numbers by which we can compare it. So that's as far as that is concerned. Right at the bottom here, I've written something called technical compatibility standard, UIC 660. If anybody has the time, now after the course, in the evening, any time, please Google and download UIC 660. It's a very small, very thin booklet, which is basically, it basically specifies the European standards of intercompatibility and interoperability of rolling stock as far as the technical design considerations are concerned, which we've just discussed. Don't worry यार, स्लाइड की फोटो मत लो, आपको पूरी स्लाइड मिल जाएगी। जैसे कि मैंने कहा, मैंने बहुत ध्यान से डिजाइन करी है। ठीक है, तो UIC 660 is basically technical compatibility. The Japanese do not publish any technical compatibility data. So, which is why we use UIC 650. It is basically a standard of comparison of rolling stock. Again, we could go on and on about boom, we could go on and on about noise distribution, distribution of sound, superstructure, bogey. I will not go into any of that.
Server 50.
Thank you. So, we've already covered all this. Now let's come to material. Shell material. Again, this is okay. Can anybody tell me what is the major grade of aluminium